but now we'll get whatever's about to unfold.
Holy shit.
One big jolly
All right.
rocket field.
Alrighty, friends. Hi. Hey. 10 minutes, 5 minutes, or whatever, later. So, number 4, all those problems were solvable on the assignment that is due today. So, if you need more time because you thought one of them wasn't exact, in particular number 4, or you thought that I'd said number 4 was not exact and it was referring to this assignment, just get it to me by Friday. Does that sound okay? Just get it to me, drop it by my office before like noon on Friday. Just pop it in there. Be splendid. Olivia, could you just like turn that, please? It's really, really bright. Thank you. And I usually like that, but cool. So the web work is now open and visible, thanks to Chris for letting me know that that was not the case. So there is a web work, but I want to do something first. I want to talk just a little bit before we do that. And then that web work, I set it due for the end of the day on Monday of next week. There's 10 problems. If we need more time, we'll add that time on. But it should be, I think it should be pretty good, especially if we get a start today. I want to just address something that we need to address. And the good news is you're not going to get homework on it because the web work wasn't open. So you'll have, I want to make sure you always have plenty to do. Oh, look at that pen. Something turned out good today. Existence and uniqueness of solutions. We've got to address this question. And I've been like ducking Kitra's question. Kitra's been asking me about this since day one. Like, how do I, when does this stuff not exist? What's going on with this? And I've been like giving her very vague answers. So I would like to give her and the rest of you a much more specific answer. So let's say we're given a pretty typical problem for us. Given the initial value problem. We've got, let's do y prime equals f of xy, and then we have an initial condition. Something that we got into this form. If, and I'm not going to prove this because to prove this actually, first off, wouldn't be informative. Sometimes proofs are helpful in helping you understand how things work. Here it would require like days of proof, and the payoff is pretty minimal. So we're not going to prove this, but we will talk about it, and I'll show you how to use it. If two things have to happen. One is that f, this function f of xy is continuous. And let's draw a picture here. So I want to describe a rectangle. Here's x naught, here's y naught, here's our initial value. I want to describe a little rectangle around this thing. So we're going to say is continuous in some rectangle R containing the initial point. And it doesn't matter what the dimensions of this are, as long as there's some rectangle that you can draw around that initial condition where f is continuous in that thing. So when we look at this, what does that mean? This z equals f of xy is a surface in 3D space. We just want to make sure there's no jumps in it, or breaks, or asymptotes that make things fly off to infinity. So, you know, very intuitive understanding of what that is. And this is the weird part, the first partial of f with respect to y of that function is also continuous in R. Bless you. So if these two things hold true, then there exists a unique solution to the problem in R. We don't know what happens outside of R, but if we can find this rectangle where this thing is continuous, its first partial with respect to y only is continuous, then the solution will exist and be unique in there. So let's talk about this, because you might not have seen a lot of stuff like this if you haven't had logic and proof, and a lot of you haven't, or you're in there now. So this is the part that is existence. This guarantees we can solve the problem. So this guarantees a solution. However, as you'll see in just a minute, just having one solution, or just knowing there's a solution there, doesn't mean it's the only solution. So this means there is exactly one solution. So this is weird, and this is the kind of thing that like you're never gonna have to worry about, honestly. Like if I ask you to solve a problem, it's never gonna be, oh, tricked you, there is no solution. Right, I'm not gonna pull some crap like that on you. Sorry, I got the wrong glasses on here, and there's twice as many of you as there should be. I don't know if I've told you, I have double vision, and it really sucks. And it doesn't look like it's gonna get any better now, because I might have left my glasses in. Well, howdy, lots of you. Wherever you are, just stumble around like Mr. Magoo. And you don't know who Mr. Magoo is, probably, because you're not that old. So, anyway, why would we care about this? Well, it does give us one great thing. So, there's an immediate corollary. And a corollary is a result that comes from a big theorem. This is really an existence and uniqueness theorem, but there's a corollary. Is that right, or is it 2 R's?
That's right.
Is that right? Cool, wow. Immediate corollary, which is really nice, is that solution curves to an ODE, ordinary differential equation, cannot intersect. This is super important, and let me just show you why. Because, so I should say, if the hypotheses are satisfied. So, why would that be the case? And it's pretty easy to see. Let's say I've got this solution curve headed through this point x naught, y naught. And this is a solution to this. Any other solution can't intersect that thing. In the rectangle where we're guaranteed, here's our little buddy R, or big buddy R, depends on all sorts of things, how big that rectangle is. But if I have another curve, it can't pass through this one at any point, because that would mean if I made that new point my initial condition, I have 2 solutions emanating from it. So let's just make a little remark here that this can't happen because it would mean multiple solutions emanate. Ooh, I've never written that word down. Is that 2 M's?
Just one.
Emanate, okay. Emanate from a shared point. So even if it wasn't necessarily at the initial condition, let's say this, the initial condition was somewhere else. If this was x1, y1, then I could just say, well, use that as my initial condition. I'm looking for the solution that goes through that point. No other solution to this differential equation could go through that point because I'll just make a new problem that says this, and uniqueness still must be guaranteed at that point, provided all this stuff's going on. So that's going to come into play a little bit later, but right now, that's our immediate payoff. Let me show you an example and a non-example. Is there any questions actually to clarify before I go off? I've just been like rolling here. Okay, cool. All right. This is the kind of stuff folks never have questions about because it's kind of heavy, and but I just want to make sure it's all clear. So here's an example. Let's say I have y prime equals y to the 1/3. And I've got this initial condition, y at 0 equals 0. So, one solution to this is just y is 0 for all time, or for all x. Make sure you see that, and let's talk about it. If I have a constant 0, the derivative of that is still 0, right? So if I have y identically 0, and I'll add that triple equals thing in there to say, damn, that thing is never anything but 0, then y prime is also 0 here. And that, when you plug in 0 here, and you plug in 0 here, that means it's a solution. So that works, but I could also go ahead, let's say I didn't even think about that, and I'm just like, diffie-q, I'm in diffie-q mode, I've solved 100 problems, I'm ready to solve more. So you just keep solving, which is probably how it feels after working on these assignments. And then you separate. And then you make that better for integration. And then you integrate, that goes to 2/3. So out in front is the 3/2. And then this is x plus c over here. Now hold on, look at this, I'm getting a new solution. So y to the 2/3 equals 2/3 x plus suck that 2/3 into the c. And then y equals, take the 3/2 power of each side. Cool, so that's actually, if we didn't have an initial condition, that would solve that up there. But also, oh, there was something subtle that happened here. When I did this, I actually took a square root. Right, do you see that? It's like a secret square root because I did a 1/2 power. So since I did that, I should have put that in front. Oh shit, already there's like multiple solutions going on. But we want to match our initial condition, so y at 0 is 0 means c is 0. So y of 0 equals 0 implies that y equals plus or minus 2/3 x to the 3/2. So it means c equals 0, is what I meant to say. All of these things solve that differential. I have 3 solutions. So right now, here's the solutions. Here's x, here's y, here's one solution. Y is 0 for all time. You can go backwards in time. Here's the other one. These things are like parabola-ish. Let's see, so that one, yeah, probably something like that, and then like that. Here's the plus version, here's the minus version. So I've got these 3 solutions coming from this point. What happened? Well, this doesn't satisfy the hypotheses. So let's take a look here. This is f of xy, and 0, 0 is my initial condition. So to guarantee unique solution existing, I need to be able to find some rectangle around 0, 0 where this is continuous and its derivative with respect to y is continuous. So this thing right here is continuous. This is no problem. In fact, this looks kind of like a weird like cube root sheet floating in space. So something like that. And this keeps going, right? So it's kind of like just to show that keeps on going. I'm also trying to show off some of my 3D skills. But we've got something like this. Let's make that over. Make the axis like that. It's coming through there. So you've got like this weird surface in 3D space. Looks like just a piece of paper just kind of bent into an S. That's what this looks like. There's no breaks in it. It's quite beautiful. However, its derivative is 1/3 y to the negative 2/3. And that is messed up right where it matters most. at 0, 0. So this isn't even defined at the initial point. Not defined. That word's defined at 0, 0. So does that mean we can't solve this? No. But it means we can't expect there to be just a one solution. Notice we could totally solve this. And we did. Take your pick. All these work. It's just no guarantee of uniqueness. So this doesn't satisfy. Let's just wrap this up. Doesn't satisfy the hypotheses. So no guarantee of a unique solution. And that's good because we don't have a unique solution. All right, I got one more example to show you and then I want to give you time to be able to work on all the stuff, or at least start on it while we're together. So then the other example is a positive example, very uplifting, emotionally supportive example. Where the hell is it? There it is. So we got x dot equals sine of tx over x squared plus t squared, x at 0 equals 1. Now you might think, boy, that looks terrible. Yeah. I'm glad I don't have to solve that. I'm glad that's just an example in class. And that would be a good, pretty decent response probably. Because that looks challenging. Let's take that hypothesis from the original thing. Remember, this is now f of tx. And let's think about how that hypothesis went. So 0, 1 is our initial condition. I need to be able to find some rectangle around this where this function is continuous and it's partial with respect to x, the dependent variable, is continuous. So we need to check, is there a rectangle about 0, 1 where f of tx is continuous and the first partial of f with respect to the dependent variable. That's why I put this example in here, so you wouldn't think it was always just y, or you saw that it's the dependent part, really. So the partial of this with respect, I already did it, I don't want to have to think through it again. Here it is. If this is f, then the partial of f with respect to x is t cosine of tx times t squared plus x squared all over t squared plus x squared squared. And then on top, there's still some more shit. It's minus 2x sine of tx. That's really sloppy writing. That's what it is. Whew. All right, sorry for the cram. What can I help with? Sorry, is there any translation needed, or was it already translated?
She got it.
Okay,
I was just asking
awesome.
if that meant continuous.
Yeah, thanks. Yes, yes.
What's in the sign? Is it just TX?
I'm sorry, what is this here? Yes, that is a TX. Thank you for asking, so that everyone can know. I'm sorry, I'm getting kind of spazzed out here a little bit. I can feel it happening, but let's see if I can try to bring it under control. So look at that top one. Where is that thing not continuous? This is the original function. Where would that not be continuous? What do you think, Thomas?
At 0, 0.
Yeah, right? Like the only thing that's bad here is this division. That the sign is good for no matter what you put in it. You can take the sign of anything. So this is all happy on top. This down here is where the trouble arises. So we just need to make sure that x squared plus t squared is not equal to 0. Notice that because of the squares, that's the same thing as saying x can't be 0 and y, sorry, no, that's not what I need to say. Let's see. Make sure that this is not equal to 0, and this is only equal to 0 only when they're both 0. That's the only way that thing can be 0 because they're both squared. That's what I'm trying to get at. So there's no cancel. If there was a minus in here, we'd have a whole lot of problems. But we don't. And so I would just set my rectangle, R, to be one that doesn't include the origin. So if I just make that rectangle any stop anywhere right above the origin, I'm going to be good to go. Same thing for this. Notice that this thing here has the same troubles. The top is totally cool with all values. It's the bottom that creates a singularity. And that singularity only arises when both variables are 0. So here we would just choose R to be any rectangle about 0, 1 that doesn't touch the origin. It doesn't contain 0, 0. And I mean, that rectangle doesn't have to be symmetric. So just as a quick note here, if I got 0, 1, I'd maybe come down to a half, but this rectangle could go up as high as I want it to. In fact, it could be infinite if I really wanted. So all rectangles are cool as long as they don't drop below the x-axis, t-axis, and we're good to go. That's all I had to say. Hans, do you have a question?
No.
No, just an inch. Cool. Isn't that nice that I pointed that out? Very nice. Does anyone in here play Dark Souls? Okay, so you've seen, I wore my Souls shirt for today. Praise the sun. Just for you guys. Okay. Let's get busy working on the web work. Or whatever you want. You can do whatever you want. I'm probably smartest to work on the web work.
Yes.
I'm going to try to find my glasses really quick.
Did you solve it? No. It's right there. Number 4.
Hopefully that web work is open. Is it showing up?
Yeah.
Yay, cool.
Okay.
Oh yeah, they're back in Carol. Okay, everything's all right. Everything's okay. Get them later. Yeah, I think I put it up. Let me check. I thought I put it up. Can anyone pop up? Anyone? I don't want to disturb anyone. Do you have like?
I can do it.
Yeah, we'll check. I just want to like check on my YouTube page, see if there's a queue.
The YouTube page.
Yeah, then don't worry about it. There's,
Okay.
Olivia and I'll figure it out. I thought I had posted the video, but maybe not. Because I even said hi to you. It's good, I see you looking up other different piece stuff, that's excellent. I think you just did it pretty good. One's that much, so yeah, that's good.
Yeah,
And then
that's-
go to videos.
Yeah, I'm gonna do it. I'm gonna do it right
Oh,
now.
dang it. I can probably fix that right now, so let me do that. But not that it mattered now, but. Okay, yeah. All right, I'm stopping.